Welcome to the AI Research Roundup. I'm Alex. Today we're looking at a paper from the Hugging Face trending list, published on February 24, 2026, just yesterday. It introduces a reinforcement learning framework that prevents agentic models from stopping their reasoning too early, allowing a video model to achieve 44% accuracy while using roughly 10 times fewer visual tokens than standard baselines. The paper is titled PyVision-RL, Forging Open Agentic Vision Models via RL, and as we'll see later, the strategy they use to achieve this efficiency is quite clever. And for those interested in the implementation, the authors have shared their code on GitHub. You can grab the 8 billion parameter weights for these image and video models on Hugging Face, along with helpful usage examples to jumpstart your own agentic vision projects. Alright, Figure 1 illustrates the architecture, which connects the multimodal large language model at the top to a Python runtime environment at the bottom. On the right, you see the interaction loop. The model generates code blocks, executes them, and receives multimodal clues back, repeating this until it answers. The critical part is the PyVision video setup in the middle. Here, the video loads exclusively into the runtime, not the model itself, forcing the agent to actively sample only the necessary frames via code. Figure 2 makes this difference concrete by comparing the two strategies side by side. On the left, panel A shows how regular video models work. They take a video, uniformly sample a fixed set of frames, and inject them all into the context window before reasoning even begins. In contrast, panel B illustrates the PyVision video approach. Here, the model uses Python code to selectively fetch and plot only the relevant frames step by step during its reasoning loop, which significantly reduces the computational cost. So with the method defined, Table 2 quantifies the results on the Versus SI bench, which evaluates spatial reasoning in video. The bottom row highlights that PyVision video achieves the highest average accuracy at 44%. This performance significantly outpaces the Huan 2.5 VL base model, which scores roughly 37%, and also beats the Agentic Vital model. The gains are particularly strong in complex tasks like object counting and approach order, confirming that letting the model choose its own frames leads to better spatial understanding. While the previous results focused on video, Table 1 broadens the scope to static image tasks. It compares PyVision image against various baselines across three categories: visual search, multimodal reasoning, and agentic reasoning. Looking at the bottom row, the model consistently outperforms the Huan 2.5 versus L baseline shown at the top. For instance, on the WeMath benchmark, accuracy jumps from roughly 35% to nearly 48%. This trend holds for agentic reasoning as well, where the method achieves state-of-the-art results on the TIR bench. Okay, having established the performance gains, Figure 5 performs an ablation study to pinpoint which training components matter most. The chart tracks the average score across 7 benchmarks as training progresses. The blue line, representing the full method, climbs the highest, confirming the synergy of the proposed components. In contrast, the red line shows the performance when the turn budget is capped at 2. The marked gap at step 600 proves that allowing more reasoning steps is essential. Meanwhile, the yellow line reveals that removing the cumulative tool reward causes learning to plateau. So, Figure 10 details the training pipeline, known as the oversampling filtering ranking framework. It begins at the top left with the prompt pool, where the system selects more prompts than the final batch size requires. These flow to the rollout worker on the right, which generates multiple interaction trajectories using the Versus LLM. Moving clockwise, the reward model scores these responses. Finally, the rollout selection module at the bottom left filters out broken attempts and ranks the valid ones, keeping only the most informative examples for the training update. Wrapping up, 2 main takeaways stand out. First, the framework effectively prevents interaction collapse, ensuring agents sustain complex multi-turn reasoning instead of taking shortcuts. Second, the move to on-demand visual processing shows that letting models actively fetch data via code is far more efficient than feeding them every frame. That's it for this episode of the AI Research Roundup. I'm Alex. Thanks for listening.